Hello there, Math 202 students. Before diving into this video about section 7.3, I just wanted to briefly tell you that this morning I had a department meeting with the other mathematicians, and Dr. Martin suggested in this meeting that if we're going to make videos like this with a slideshow essentially, that we should do a split screen sort of setup where you see the slides and you also see my face so that you can watch me talk. The claim is that doing this would help the professors stay more connected to their students, and that might be the case, but I should say that the longer I'm locked in the house with my two children, the worse I look. And right now I just look like hell. So I don't know that video of my face would help you stay connected to me in any sort of meaningful way as we are moving through these slides. So if you want to see my face, we can FaceTime or whatever. All right, so the goal of section 7.3 is fairly straightforward. In this continuation of linear algebra material that we are doing, I want to define and show examples of what are known as eigenvalues and eigenvectors. I'm doing that because we need those concepts to go back to the calculus in section 7.5. So I should say that in all of this material we're doing now, I'm trying to pare them back to their bare basics. I'm just trying to get to the sort of core of material that we need to understand the differential equations material that I still want to cover. This is difficult because there's lots of material I would like to show you that I would have shown you, but I'm having to cut some of it out. So as we move through these videos, if you pay very close attention, I think you can pinpoint moments where parts of my soul die. And in this video, there will be several such examples, so stay tuned for that. All right, so to motivate these concepts, I just want to start with the matrix A, and here are several vectors, A, B, C, D, E, and F. I want you to do these calculations, these 6 calculations. Do big A times little a times little b, and so on. And what I want you to think about while you're calculating these is think about A as sort of a machine that's being fed this little a, or a machine that's being fed this little b. You kind of feed the little a into big A, and you get a result. Right? After you do the multiplication, you get an output. Same thing with little b and so on. So I want you to think about the relationship of those outputs to the inputs. So after you feed little a into big A, what relationship does the output have to little a, to the input, if any? And same thing with all of these. So pause the video now and calculate these 6 multiplications. All right, assuming you're back, partially I wanted you to do those multiplications just to have some extra practice with multiplication of matrices. Here are the results. So if you feed little a into big A, you get 5, 7, that vector. Feed little b in, you get 3, 0, and so on. Notice that the output here, this 5, 7, and the input 1, 3, don't have much relationship to each other in any meaningful sense. Unlike, by contrast, think about this input of little c. When you feed the vector 2, 2 into the matrix, you get 6, 6 back. Okay, 6, 6 is a multiple of 2, 2, right? You just multiply everything by 3. So you fed little c into this machine, and what you got back was a multiple of c. And same thing with d. You fed d in there, and you got 15, 15. That's a multiple of 5, 5. And again, the scale factor is 3. So for both little c and little d, when you feed them in, all you're doing is scaling them by 3. Little e and little f, when you feed those guys in there, they don't change. They don't change. So they are being scaled, if you like, but they're being scaled by a scale factor of 1. Right? Scaling things by 1 leaves them alone. Okay, so what's the point of this exercise? There were 6 vectors we fed in. Little a and little b, when you feed those guys in there, their outputs don't have really any relationship to the original vectors. In particular, their outputs are not multiples of the inputs, right? 5, 7 is not a multiple of 1, 3. However, 15, 15 is a multiple of 5, 5, right? Scale factor of 3. Okay, so after all that discussion, these scale factors I discussed, you can scale vectors by 3, scale them by 1. Those are called eigenvalues. Vectors like 2, 2, 3, 3, 4, 4, 4.5, 4.5, 8.5, 8.5, whatever, right? Vectors that look like this, same number down below. Those are called eigenvectors of 3. if you feed any vector like that into the matrix A, and again, by feed I mean do big A times this little this vector here, what will you get? You will get 3 times the original vector, just like we got with little c and little d. So if you fed 9, 9 into this matrix, you would get in the end 27, 27, etc. 1 is also an eigenvalue. There are some vectors you feed into that matrix A, and they are just left alone. So vectors that look like this, number and then it's negative down below, those are called eigenvectors of 1. This is the idea of an eigenvalue and eigenvector. An eigenvalue is a scale factor. Sometimes when a matrix A sees some vectors, all it does is scale them. That's the effect that A has on them. So here we scaled by 3. These two guys here, you can also scale by 1. So eigenvalues are like these scale factors that the matrix A might have, and then eigenvectors are just the corresponding vectors that get scaled. So anything like number gets scaled by 3. Anything that looks like negative number gets scaled by 1. That's the idea of eigenvalues and eigenvectors. So here's the formalism, or something slightly more formal. If A is a matrix, a vector V is an eigenvector if, when you feed V into A like this, you do A times V, you get a vector that's parallel to V. The output is parallel to the input. What does it mean to be parallel? It means this, that all you've done is you've taken your input vector and scaled it by some constant. Lambda is just the scale factor. So lambda was 3 or 1 on the previous slide. Okay, and then just to reinforce, right, what do I mean by parallel? If vector V lies on this line, so vector V has like slope m or whatever, right, in the xy plane, then AV also lies on the same line. Okay, so the output vector has either the same slope or it's been reflected. Okay, so if you're on the line y equals x, say, your vector could have been flipped over the origin. Right? You just have to stay within that line, is all I'm saying. That's what an eigenvector is. An eigenvalue is just this number lambda, basically. So if b is an eigenvector, then by definition, there must be some scale factor so that a times b is, again, just b but scaled some, right? That scale factor is called an eigenvalue. Okay, there are 2 theorems to know about eigenvalues and eigenvectors. Let me just put them both up. First theorem, if v is an eigenvector of lambda, then so is any other multiple of v. Okay, so in other words, sorry, this is a typo. If this should be a bold V here. I apologize for little typos like this. It's not worth me like stopping the video and redoing it, I don't think. So sorry. If little v here is an eigenvector of lambda, then so is number times v for any real number a. Okay, so what am I saying? Back here on this previous slide, 2, 2, right? That was an eigenvector of what? Of 3, right? So will 4, 4. So will 8, 8. So will 10, 10. So will 20, 20, whatever. You can scale this vector here, this 2, 2, by whatever you want. It's still going to be an eigenvector of 3. Okay, furthermore, the eigenvectors corresponding to a single eigenvalue are all parallel to each other. So basically what that means is that a times v, those are all the eigenvectors of this lambda, for us anyway. So upshot, if you know one of the eigenvectors of lambda, then you know all of them for us. Okay, so the second theorem is that if A is an n by n matrix, then A has at most n eigenvalues. The reason is that eigenvalues come from solving a polynomial equation of degree n. So for example, if you have a 2 by 2 matrix, then finding the eigenvalues reduces, it turns out, to solving a quadratic equation, an equation of degree 2. So we all know, right? Quadratic equations have at most 2 solutions. Or exactly 2 solutions if you want to double count things, you know. Anyway, those are the 2 things to know about eigenvalues and eigenvectors. So here's an exercise for you. Let A be this matrix here. For each of the vectors below, determine which are eigenvectors of A using the definition. Based on your calculations, I want you to then tell me all eigenvalues and all eigenvectors of A. So pause the video and do that. Okay, assuming you're back, let me show you the answer. Lambda 1 equals negative 5 is an eigenvalue, and its eigenvectors look like this. Negative A and then A. So this little A vector here, when you fed it into matrix big A, what you should have then gotten was what? 10, negative 10? You should have scaled this dude by negative 5. Okay, similarly, lambda 2 equals negative 3, that was an eigenvalue. Right? Why is that? Well, when you fed 3, 3 in there, I assume you got negative 9, negative 9. It got scaled by negative 3. So anything that looks like this, number and then the same number down below, those are eigenvectors of negative 3. Okay, so you could now ask, oh, well, negative 5 and negative 3, are those the only scale factors that work like this? How do we know there aren't more of them? And the answer is by this theorem here. A 2 by 2 matrix has at most 2 eigenvalues. So in this case, we've like stumbled upon 2 of them, right? There's an eigenvalue, there's another one. So we know we're done now, right? There were at most 2 eigenvalues. And once you know them, you get their family of eigenvectors and you know everything. Okay, so after this video, you should basically be able to do this. You should be comfortable with the concept of an eigenvalue and eigenvector, and you should be able to do an exercise like this. That's what the homework over this section looks like, just to reinforce what these concepts are. Because again, we'll need these concepts when we go back to solving systems of differential equations. So I would have liked to do more in this section, but this is just like the bare bones, sort of bare minimal concept stuff to allow us to return back to the calculus in section 7.5. So the next video is on section 7.5.